All right, let's go ahead and get started. So I apologize for the sunglasses. I had my eyes dilated this morning, and I still can't see very well, so that's why I'm wearing sunglasses. But anyway, so did everyone see the announcement about online tutoring with Kevin Colhane? So check out Blackboard. Now I was trying to follow his instructions, and so he said he hasn't seen a lot of students, and I noticed that when I went down to the tutoring center, it seemed like they were trying to shift you guys to like Western online tutoring services or something. Those of you that have been down there, you can tell me yes or no, or maybe you haven't needed tutoring or you're just fine. But there should also be tutoring through your like My Rogue account, and there should be a link to free Zoom tutoring. And so if I go to the tutoring services website, so that's just roguecc.edu, and then tutoring, so academic success tutoring services. So it says online Zoom tutoring, and I think you have to log in through your My Rogue. So I don't have a student account, but apparently once you log in there, it should be there. Online classes, tutoring center. And you can always email, and you can also maybe email Kevin Colhane directly. So if you still have issues, just let me know, and I can give you Kevin Colhane's contact information. But he would be the one that you want to contact for tutoring online. And then, of course, I'm available, so just make an appointment. I'm usually available before or after class, unless, of course, I have another class, but I'll try to squeeze you in. You can come to my lab, even my 221 lab. You know, if you have questions, just stop by and see me. All right, other questions about anything? So I'm slowly working my way through your grading. So probably have more papers to hand back on Wednesday. I have a few popcorn labs today. So let's start Chapter 4 then, of covalent bonding. So last week, right, we did ionic bonding, so that was metal plus nonmetal, and we said that they were just held together by those electrostatic forces. And so now we're doing covalent bonding, where we actually do have sharing of electrons. And so electrons that are shared by atoms are called bonding pairs. And then electrons that are not shared by atoms but belong to a particular atom are called lone pairs, also called non-bonding pairs. And I'm just going to redraw this representation of water. So you can draw this a couple of different ways. Actually, before we get to this structure, let's just start with our Lewis dot structure of oxygen. So how many valence electrons does oxygen have? Look. 6. And so, right, make sure you draw them out. So they're in your Lewis dot structure, 1, 2, 3, 4, 5, 6. And so this is already showing us some information. Right, we have these two lone pairs of electrons, so these are going to be shared. And so, right, they want to make a bond here. And then if we draw in hydrogen, so hydrogen, Lewis dot structure, so there's 2 of them. And so when we're making our drawing, you want to keep a count of how many electrons you have, or how many people are coming to the party. So we have 1, 2, 3, 4, 5, 6, 7, 8 electrons total. So 6 from oxygen, 2 from each of those hydrogens. And then we're going to see how we come to that structure. So I'm just redrawing. And so usually when you construct molecules, so you want your center atom to generally be the most electronegative if you can. You don't want hydrogen in the center, so usually that doesn't make sense. Hydrogen can only make so many bonds, and so we'll see like phosphorus, sulfur, those are usually in the center. They can make a lot of bonds. But then the halogens, so they can only make one bond unless it's kind of a funky thing. Then halogens can kind of bond with each other. And so now we kind of start constructing everything. So I've just redrawn oxygen. So now we can pair on our hydrogens and where they're going to go. And so we can see hydrogen brought one electron to this bond, oxygen provided the other. So now we just have a covalent bond there. So I'm just circling them. And so again, those would be our bonding pairs. And then sometimes we note these lone pairs, so just kind of drawing these bunny ears around them. And that's just showing that these lone pairs are occupying space. So they take up a lot of space. They're very electronegative since they're just two lone pairs of electron. And so they need their space. They need their electron density. And so this also tells us about the geometry. So we'll be looking at the geometry. And so you can see from these lone pairs, it gives us a bent geometry. But we'll look again at the geometry a little closer. Yeah.
Would a molecule be the same thing as a covalent compound?
Yeah, so the molecule means it's like all discrete then, that's the structure, so it should all be covalent. And so now we can kind of explain the diatomics and why they exist as the diatomics. And so let's look at H2 first of all. And so hydrogen, if we draw its Lewis dot structure, we know it's just H with one electron on it. So it's not happy, right? The duet rule is not satisfied. And so that means if it sees another hydrogen, they just go ahead and form a bond. So I'm drawing this half arrow notation showing one electron is moving. And so that gives us our hydrogen bond. This also tells us why the halogens are diatomics. So we could draw bromine or fluorine, any one of them. And so again, octet rule, not satisfied, so it just has one lone electron here. But again, this is kind of telling us wants to make a bond. So lone bromine would not be stable like that. You would not find that. And so that's why, again, elemental bromine then. So two bromines come along. So they both want to form a bond. So now those will come together and make our bromine molecule. And so again, we haven't lost any electrons, so we started 7 from this bromine, 7 from our second bromine, so we have 14 total. So count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We have one single bond, and so this bromine is satisfied, right? It's feeling 8 electrons, so it's satisfied by the octet rule. And then our bromine on the right, again, feels all these 8 electrons, so they're both sharing that one bonding pair. And then this one, of course, 1, 2, 3, 4, 5, 6, 7, 8. And so the next thing is, well, how do we predict the type of bond, whether it's going to be ionic or covalent or polar covalent? Bless you. And we have this scale. So did we go over electronegativity in here? Or like periodic trends? So I kind of mixed my two classes because you covered the same things. All right, so let's look at this periodic trend. of electronegativity. So all electronegativity is, so let's first define what it is. So electronegativity, the key point about this is a measurement of how much an atom is pulling in a bond. So basically measurement of how much an atom draws electron density towards it. Again, that's key, is that it's in a bond. And so why I keep emphasizing in a bond is because it's really similar and follows the same trend as something else. And so I'll put that as kind of an aside. I just want you to be aware of it. So the other term is electron affinity. And it's basically how much does a metal want an electron, which is really similar to electronegativity. There's just a small little difference. And so electron affinity is a gas phase reaction. So you would have a metal plus an electron is launched at it. And then what is the energy associated with making that? If that's favorable or not favorable. And so the only funny thing is with electronegativity, so fluorine has the highest electronegativity. So it always pulls the electrons towards it. But in electron affinity, chlorine has a greater electron affinity. And that's probably just due to chlorine having a slightly larger radius that it can formally hold that negative charge better. But they're really similar. It's just electronegativity is in a bond, so it's measuring in a bond. And electron affinity would be a gas phase reaction, shooting it with the electron. So they're like almost the same thing. They follow the same trend, very similar, but small difference. And so what we find is electronegativity. So the trend increases across the table. And also increases as you go up. So again, star fluorine, and so it's just made on this scale. So they were calculated by Linus Pauling, and he determined from his scale that comparatively fluorine is about a 4 in electronegativity, so 3.98. And then, so one of the lowest ones would then be francium, so 0.7 for its electronegativity. But then we can roughly predict the bond. And again, this is just a general guideline, but we can say that if we have a small difference in electronegativity, for example, with a chlorine bond, so this would work with chlorine, bromine, fluorine, where it's the same and they have a small difference in electronegativity, or again, other elements that may be really similar. Then you have what's called a pure covalent bond. And so you just take the difference, and if it's less than 0.4, you generally consider that covalent bond. And then once it's greater than 0.4, then that's considered a polar covalent bond. So if we look at the example of hydrochloric acid, let's do the math for that. So we just have to take the difference. And so on an exam, you'd have to be given a chart or given these values. You would never be expected to look at them or memorize them, I mean. So then we have chlorine, so 3.16. And then hydrogen, 2.1. And you just subtract them. So you get 1.06 for their difference, and so that falls right in the middle of polar covalent. And then once you have a large enough difference, so sodium chloride, if it's greater than 2, that means it's an ionic bond, so completely separate. And so it's kind of considered, a spectrum too. There's some long bonds where people can debate, are they really bonds, that sort of thing. So there's always fun things to discuss in the research area of chemistry and bonding. And so let's do the, oh, yeah.
I might have a silly question, but when you're saying it increases electronegativity, are you saying it increases the negative charge or just whatever charge it is?
So it increases the value of the electron negativity, and that would also mean that it's physically pulling more. And so, and I'm not the greatest artist, but you have, like, you're kind of measuring this electron density, right? So then the more difference that it gets, so it starts off equal, where it's like a nice even bubble, and then as it pulls it more, it's like the bubble gets greater. So you could say for HF, right, the fluorine would be grabbing like a large amount of electron density, and then so versus sulfur, we would still be pulling it, but not as dramatic. And again, I'm a horrible artist, so apologize. But you could, so how you could look at this, like, without me just telling you and scribbling, there is like computational software, so you could look at that, look at the modeling, and then it tells you and kind of compare the electron density, tells you the mapping. So then let's just practice sodium chloride so we can see how we can determine an ionic bond. So from the chart, so we had said chlorine was 3.16. And so let's look up sodium, so 0.93. And let me get out my calculator. I guess I don't need a calculator, so 3, 2, 2. So 2.23 for the difference, so that's greater than 2. And so that tells us, okay, that's an ionic bond. And so there's, again, kind of the continuum. And so now we'll just kind of formally define the different types of bonds. So normally, we just expect things to make a single covalent bond. And so when two atoms share one pair of electrons, that's just called a single covalent bond. So again, 2 electrons, 1 pair. So just like we saw on the oxygen water example earlier. So we can have our oxygen, and it also says, so one atom may use more than one single bond to fulfill its octet. So all that's saying, right, is oxygen made 2 bonds. And we'll learn that carbon can make 4 bonds, and we'll even learn about expanded octet. And of course, hydrogen follows the duet rule. And so now let's look at a double covalent bond. And so we see this in O2, but let's go through this, how we would predict it. So back to our diatomics. So right now we're staring at kind of 2 Lewis dot structures of oxygen. And then how many bonds does oxygen want to make again? Yeah, so it will make a double, yeah. So it wants to make two bonds, right? Because we have one lone electron, the other lone electron. So if there's two oxygens, you're going to have them both coming together to make a double bond. So that would be the Lewis dot structure of oxygen. And so oxygen is pretty cool. And so other elements that can double bond with either each other or themselves. So I would highlight this. So carbon, for sure we see that. Nitrogen can make some double bonds. And then oxygen, sulfur, phosphorus. So those all like to make lots of bonds. Let's see. I guess I'll mention it now because we don't talk about orbitals in this class. But what's really cool about oxygen and this structure is that eventually you could also apply MO theory to it. And it would also explain why oxygen is paramagnetic. So that's kind of a fun fact for y'all. And so you can also have where two atoms share 3 pairs of electrons. And so let's look at nitrogen and its Lewis dot structure. So judging from its Lewis dot structure, so how many bonds do you think nitrogen will want to make? So 3, exactly. So, right, these 3 lone pairs of electrons. And so if it's just looking at itself to bond, then how many bonds do you think it would make? So 3, so giving us a triple covalent bond. And so again, count your electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you brought 10 electrons to the party. And so you should have 10 in your final structure. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that all works out. And then we, of course, have our octet. So our left nitrogen, 1, 2, 3, 4, 5, 6, 7, 8, satisfied by the octet rule. And then our other nitrogen, so 1, 2, 3, 4, 5, 6, 7, 8, so both satisfied by the octet rule. And so triple bonds are less common, but carbon, of course, can triple bond, especially with itself. And then sometimes you see nitrogen triple bond. Oxygen, it happens, but not as much. And sulfur, same thing. All right, so now we're gonna go over the characteristic examples and what these elements tend to do. So we'll start with our group 4 and just kind of characteristic compounds. And so they tend to make 4 bonds. So we can see that from carbon. So carbon, remember, had that special Lewis dot structure where we drew it like this to kind of indicate that, yes, carbon likes to make 4 bonds. And so methane is generally our characteristic compound. So I'm also trying to draw it in 3D. So our carbon is in the plane of the board, hydrogen is in the plane of the board. This hydrogen is still in the plane of the board. Then I'm drawing a wedge to show that this hydrogen is coming out of the plane of the board. And then I'll put a dash for my fourth hydrogen to show that going behind the plane of the board. And so group 4 tends to make a lot of these compounds, so silicon tetrachloride, germanium tetrabromide, so other things to watch out with group 4 is so carbon can make double bonds. So this is pretty common. So carbon double bonded to oxygen, and then you could put hydrogens there, or it would go on to bond with other carbons. So those are kind of the two characteristic things. So then group 5, we draw our Lewis dot structure. So how many bonds do we say they like to make again? 3. So I want to make 3 bonds. There are 3 lone pairs of electrons. And so that's what they do. So kind of the characteristic compound is ammonia. And so this also tells you kind of more about the group as well, so we can tell that it's reactive. So we have these 2 lone pairs, so they're still primed to attack. So of course, you know, ammonia is a really strong cleaning agent. And so phosphorus, although phosphorus gets weird, but it can be happy with 3 bonds. Except, does anyone know what this is? It has a special name. May not know it because it's its common name.
Is it a polyethylene?
No. So this is just called a phosphine, but they're pretty nasty. So they're very reactive, very water reactive. So they would react, you would open them, they smell horrible, start immediately reacting with the atmosphere and making double bonds with oxygen. So it would go on to react. Oops. So this is kind of skipping ahead because I haven't told you that phosphorus can do expanded octets. So pretty nasty compounds. But again, all of group 5, they tend to be pretty similar. So there would also be PCl3 or phosphorus trichloride. And so of course you also have arsenic in that group. So again, same characteristic compounds. And so group 6, so how many bonds do we say they like to make? 1 or? 2. So group 6, they like to make 2 bonds, or at least. And so we see this best if we just go down the group. So we have water. We could also do, so we do CO2. Let's look at CO2. So CO2, we can piece together. We know carbon likes to make 4 bonds. Oxygen likes to make 2. So now they kind of come together like this. So if we compare sulfur, so we can make hydrogen sulfide. So just comparing. And so this is not smelly, this is really smelly. And they get smellier as you go down with those compounds. And so we'll later learn these are all taking a bent geometry too. So they all have those lone pairs. And then comparing, so carbon would do the same thing with sulfur. So CS2, carbon disulfide. And selenium would do the same thing. And so just for fun facts, so of course CO2, you know you expel CO2, but then the heavier analogs, so they can become poisonous and dangerous. So carbon disulfide is dangerous since it's heavier than CO2, so your body has a harder time expelling it. And then the other thing is, I think the binding coefficient of CS2 is stronger to the hemoglobin compared to CO2, so it's also harder for your body to remove it. So if you were ever exposed to CS2, you'd want to get monitored right away, go to a hospital, check your oxygen blood levels, and then potentially receive oxygen therapy to help expel that. And at the very least, you might feel like you have a hangover or something from the CS2 exposure. Yeah.
What usually expels CS2?
Sorry?
What usually expels?
Oh, just like breathing and time. So like it is, your body has to work harder since it doesn't just readily fly away. So you'd have to be like kind of coughing, and your body, I think, eventually metabolizes it, like overnight. And I know, speaking from not me personal experience, but my lab mate personal experience. So.
Where does that come from?
Oh, if you're like working with CS2.
Oh, okay.
Yeah. So people will do research with CS2 because it's similar to CO2. So if you want to save the world, right, from mean, naughty greenhouse gases, then the idea is you take CO2 and do something cool with it. So that was my research. But if you can't do something cool with CO2, sometimes you try CS2 just to get it to do something. And then my lab mate breathed some in her face while cleaning. So it's always while cleaning. That's the other thing. It's never while doing the cool experiment when you're cleaning up after you expose yourself. So let's look at group 7. So what do we expect for group 7? How many bonds will they make?
1.
So 1. This is 1 bond expected. And so we'll look at a couple of funny ones. So we saw, of course, all the or at least the halogen diatomics follow this. So fluorine, chlorine, bromine, and iodine. So that explains all of those. And then acid, so like HF, that would be a covalent bond. What else do we have? Or with, again, silicon tetrachloride, so they're just making one bond. I did not draw that tetrahedral. It's going to bother me. So those are kind of the basic rules. So let's kind of recap for a second. So right, we have our Lewis dot structures. You kind of want to draw them. It gives you at least like a starting point of what to put together, and then just keep track of your electrons. So how many they're bringing, again, from the valence number of electrons. So it always should be easy. Follows the groups and the patterns. So keep track with bookkeeping. So keep track of electrons. Now let's look at kind of funny scenarios, expanded octets, and other geometry things. So first of all, before we get into expanded octet, I just at least want to make a remark because I'm pretty sure your textbook has it wrong. And so with the expanded octets, they do not invoke d orbitals. And so now I'll go on a quick rant. And so most textbooks say this all the time. So the rule that they always like to say, let me grab a periodic table. But they always state, oh, once you get to the third row, now we can have expanded octets, and that's because they have d orbitals and the other ones don't. And while that seems true, it's not what's actually going on. So we're at 1s, 2s. So they're saying, right, that the 2p's, that they don't have d orbitals, so they can't actually bond. And the real explanation is this row is just simply too small, like the radius would not fit. And so people have done experimental studies, like theoretically on NF5. And so the problem with NF5 is it physically can't fit everybody around it. And so the only way it would work is if it had unnaturally elongated nitrogen-fluorine bonds. And so that's the only way it fits in there. So it's theoretically possible, but of course this would be really unstable even if you could isolate it. But again, it could totally do it if it could physically fit those fluorines around it. And so what we actually find is that the p orbitals are enough. And so if you're interested in learning more and want a full detailed explanation, I'm more than happy to provide it, but it kind of just goes beyond the scope of the course. But you really find that the d orbitals are not accessible for all these p orbital interactions. All right, so now that we've got that out of the way, let's just look at some examples. And so group 8, we said those are noble gases. We don't generally expect them to react, but of course chemists, that's what they want to do. They want to force exceptions and reactions. And so xenon, it has a pretty large radius. And when you draw this, make sure, right, it's bringing 8 electrons to the party, but we can react it with 2 equivalents of fluorine gas and then, or excuse me, 1 and 2. And so we get 2 different compounds. So we can make xenon difluoride. I don't know why I put it, I don't know what I drew here. And so you just want to make sure you bring all your electrons to the party. You're just, again, also following your rules. So you know fluorine's probably just going to make one bond, so start with that. Right, you know your fluorine has to bring 7 electrons each. And so do some accounting. So 7 plus 8. So how many total electrons do you have in this system? When did you say 22? Yeah, 22 electrons. And so then just start filling them in. So I would start with the fluorine since we know they're probably not going to go expanded. They don't tend to do that. So give it an octet. Now see where you're at. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Then put the remaining ones on your group 8 one or whatever your central atom is and see how that looks. So 16, 17, 18, 19, 20, 21, 22. And so that looks good. And that also makes sense for its geometry. So it has these orbitals here where the lone pairs would be occupying in the center, kind of spread out in thirds. These are going to be going along what I would say the z-axis or in the plane of the board. So this is a linear molecule. So if we put xenon tetrafluoride, so let's guess what that would look like. So again, do your accounting. Just start sketching it out. So 7 times 4. So we have 28 plus 8. So how many electrons? 36. And so again, just start drawing xenon in the center. It makes sense to just draw at least one bond to each fluorine, right? We know that's what fluorine wants to do. Then I'd fill in the octet for fluorine. So now we have 8 times 4. So 8 times 4 is 32, and then 33, 34, 35, 36. And so this makes sense with what we know about the geometry. So this geometry, don't need to know it, but it's square, planar. And so these fluorines would kind of be just in a plane with the xenon, like a flat piece of paper, and then the electrons would be above it and below it there. I could try to redraw that in 3D. Again, I'm a terrible artist. So my wedge is coming out of the plane of the board, dash is going behind, so you can kind of see it 3D. So both ways, just different orientations.
So do electrons like to typically be in pairs then?
Yeah. So you generally don't have just one lone electron. So one lone electron is called a radical. And radicals do exist, but they're usually short-lived. I don't know if you've heard of radicals before. Like a buzzword for health, but they do have some point. And your radicals will react, but won't go into health. All right, so let's look at more expanded octets. And so back to group, so we were back to group 5 here. So we said that this is theoretical, but so PF5 does exist. So phosphorus pentafluoride. And again, with those, keep track of your electronic bookkeeping. So 5 electrons for phosphorus, and then fluorine, so 7 times 5, so 35 plus 5, so how many electrons? So 40. And then you can just start off again, drawing your structure, kind of what seems reasonable. One bond to everybody. I'm kind of drawing it in 3D, what we expect it to look like. So this fluorine, this phosphorus, and this fluorine, so these are all what are in the principal rotation axis, so up and down, Z. And then these are kind of in a plane, in a triangle form, spread out. And so the name of this would be trigonal. This is a triangle, and then bipyramidal, or bipyramidal. I can't spell. And so just bipyramidal, so 2 pyramids. So you draw 1 pyramid, 2 pyramids. And so arsenic could also do the same. Again, you see it with the halogens or other elements. And so let's see what else phosphorus can do. So let's look at some of your polyatomics. So phosphate, do you remember what the formula is for phosphate in the charge? PO4 -3. And so now if we want to draw something that's not neutral, we have to take into account the charge on it and what to do with that with our electron bookkeeping. And so let's just start. So phosphorus, and again, you always do the neutral valence first. So phosphorus brings 5 electrons. Each oxygen has 6 valence electrons times 4, so 24. And then this -3 charge means that we added some electrons. So that means we're going to add plus 3 electrons to that. So if you had, maybe we'll do ammonia in a second. So for ammonia, right, you would have to subtract an electron then. We'll practice with that one. Let's go back to phosphate for now. So we have 5 plus 24 plus 8. So how many electrons? 32. And so sometimes we may not know where to start. And so again, first thing, I would just start putting a bond to each oxygen. And then you can assess. So I have 8 so far. Well, I could just do this, so I could fill in the octet. And let's just see how this looks. And so now we need to do an evaluation. What I mean by that is you should always calculate your formal charge, but usually it doesn't matter. And so let's first define, well, what is your formal charge? So your formal charge is you just take the number of valence electrons, so that's from the periodic table for that element, and then you subtract the number of bonds, and then you subtract the number of electrons, so like individual electrons. And so sometimes you see little variations on this formula, like you'll see like number of bonding electrons divided by 2. That's the same thing as the number of bonds. And so let's do this together. And so the other thing about the formal charge is we haven't really worried about it because it hasn't come up. So your formal charge should always equal the charge of the molecule. But previously we were just looking at neutral molecules. So it kind of made sense that we didn't really look at it. And they were all doing kind of normal bonding scenarios, nothing, no multi-electron here, no hypervalent. So nothing was too crazy. But now that we're looking into kind of different bonding scenarios, we have to do this evaluation. And so we expect there to be a charge somewhere because there's a 3- charge. So it has to be located somewhere on this molecule. So let's figure out where. And so let's just start with 1 oxygen. They're all the same. So whatever 1 is, they should all be. And so for my formal charge, how many valence electrons does oxygen have? So 6 minus, and then so how many bonds does this oxygen have? So you're just looking at the individual oxygen. So -1, and then how many individual electrons? So 6, right, 1, 2, 3, 4, 5, 6. And so what do you get for the formal charge? So -1. And then all these oxygens are the same. So you can see, okay, that's 6 -1 -6. And so we can write a little -1 around them. Uh-oh, we have 4 though. Well, let's check phosphorus really quick. So phosphorus, how many valence electrons? So 5 minus how many bonds? 4, so 1, 2, 3, 4 lines to it. How many electrons? How many lone, just like lone electrons on there? So it should be 0. And so that gives us a +1 formal charge. And so there's a couple of things about this. So first, we're seeing, all right, well now I at least have a -3 charge, so that looks good. But there might be another structure we can draw. And so that's your other hint, is anytime you see a positive charge right next to a negative charge, then that means we can probably draw another structure. And so first I'm going to redraw this, just so it's clear, and then I'll indicate the electron action. So we're here. So again, highlighting, I got a negative charge right next to a positive charge. I ideally want to get rid of these charges. And so the action always has to come from the electron. We can go ahead and move these 2 pairs, and you want to move them as pairs, and then stick them in a bonding pair instead. And so now I'm just going to redraw my new structure. So now I have a double bond on one of those oxygens. The other 3 will still have a single bond. And so I'd want to put my negative charge, because these still have a -1 formal charge. But we eliminated our formal charge on the phosphorus, so now it's 5 minus 5, so that's good, it's 0. This oxygen now has a 0 formal charge, that's nice. We still equal overall -3, so that looks good. And we still have 32 electrons, so everything looks good there. And then we can also note, So how many total electrons does phosphorus have? So how many does it feel? It should be greater than 8 since it's expanded octet. So you're just looking,
Wait, how many total electrons does phosphorus have?
yeah, so you're just looking at the ones that it feels. So it should be 10, right? So you're just looking, because it came with 5, then it bonded, right? Then all these things happen to it, but then you're trying to see, well, how many is it directly tied to that it feels? And so you have that it feels these 5 bonds. So that'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we would say that phosphorus has 10 total electrons. And all these oxygens, so they're all satisfied by the octet rule. So 8, 8, 8, and 8 for those. So just watch the language. So you have 32 electrons total in your system, but then phosphorus is feeling only 10 electrons. And so we can say it's greater than the octet rule. Yeah.
I just have a question. Could you explain again why it would have -3 charge?
So that was just from the phosphate. So we had said that this is, what we're looking at. And so we're just kind of finding, right, that these polyatomics exist, and now we're kind of seeing why they have that -3 charge, is if you draw the structure, it got some electrons from somewhere. More questions about this? So let's do ammonia, even though it's not an expanded octet, but let's just cover it. And I'll take a couple of minutes and ask your partner, ask your friend, right? Do your little bookkeeping. Don't forget to subtract your electron, and then just draw your structure for ammonium. And so this is ammonium. do we have a structure? I guess, how many electrons do we have in this system? So how many did nitrogen bring? 4? So don't subtract anything yet. So 5, and then how many from hydrogen? So 1 times 4. Then we have the plus charge, and we have to subtract 1. And so now we have, I heard someone say 8. And then what did our structure look like once we drew it out? Anyone describe it? So we should have nitrogen in the center, and then just hydrogens around it. I was drawing that in 3D, that would be better. And then a little plus charge. So formally, it's carried on the nitrogen. So you could draw a little plus charge indicating it there as well. And so just think back to ammonia. And so this would be the base, and then this would be your conjugate salt, which we'll get back to this actually at our last chapter, acids and bases. But you can at least, get a little appreciation of the reactivity and their interchangeability there, how one becomes the other. So ammonia becomes ammonium. All right, let's see if we can finish up with our expanded octets. So let's look at group 6. So I think we might have mentioned sulfur hexafluoride in this class, but I didn't. It's just a really dense gas that changes your voice to lower if you were to breathe some in. So you can breathe in helium, right? Helium's less dense, so it makes your voice high-pitched. And then breathe in a little bit of this, makes your voice low-pitched. Again, be very careful. Disclaimer, when inhaling gases, you could accidentally suffocate yourself. So sulfur hexafluoride, this would be its structure. So octahedral.
Triple and single bonds?
Oh, sorry, these are all single bonds. I just drew dashes and wedges to show. And so let's take a couple of moments, see if you can do sulfate then. So you have your polyatomic SO4 2 minus. So what would that look like? We have a sulfate structure. So how many total electrons are in here? 32, so 6 from sulfur. 4 times 6 is 24, and then 2, so 32. And then you could start drawing one bond to each oxygen, but then what did you find with your formal charges, perhaps? So how many oxygens need double bonds? 2. So 2, so if you put 2 with double bonds, and then fill into 32 electrons, you have 8, 8, 8, 8, and then these 2 oxygens have a formal charge of -1, so 6 minus 1 bond minus 6 electrons. So we have that same -1 formal charge. You could have started with a single bond at each oxygen, and if you did the formal charges, you would have like a sulfur 2+, and that would be a little odd. And then how many total electrons does sulfur have? So 12 total electrons. So again, that's why we say it's hypervalent. What else do we want to say? Oh, and the other thing I didn't emphasize enough is so we can draw, again, what are called, so these are all just resonance structures. And so I'll draw this since it's not necessarily wrong. So we could have started with this structure. So 2+, put your formal charges. But then you'd also just want to be able to draw all the other permutations. So just emphasizing it doesn't matter where the double bond is, because really it's kind of an average of all these structures. So we can make these ones single now. You could alternate them. And so you would find in reality it's kind of an average, so you would add up all your bonds. So you have 1, 2, 3, 4, 5, 6 bonds divided by 4 things. So that's, everyone is about 1.5 bonds roughly, and that would match roughly with the bond length, so you can kind of predict that. So it's not quite a single bond, not quite a double bond, and so that double bond would be a little bit shorter, somewhere in the middle.
When you're adding the, because you're adding the 2, the -2, how do you know which one to add it to?
Oh, I just add it at the end, but then here it's just by the formal charges, so that's how I know where to stick them. So if you started, so I say like start this, because this is like the simplest structure. Like you don't know anything, I'm just going to put sulfur in the middle, draw a line, and see what happens. And so if you just draw 1 bond to everybody, and then fill in the electrons, but
And then do the 2, okay.
yeah, but then you would do the formal charges, then you'd see, oh, I have a negative next to a positive, and another negative next to a positive, maybe I want to draw some double bonds. So then ideally you're trying to get rid of formal charges. And we'll do more practice too. And so let's finish up at least with the last bit. So I3. So what might this look like? I'll give everyone at least a minute or two. How many electrons? I'll give a hint, it's not like a ring or anything, you have a central iodine.
And it's neutral, right?
Yeah. So how many total electrons do we have?
28.
So 28. You have a question? Or?
No.
And so I'll just try to stick iodine, 3 iodides around it, fill in the octet. Then how many lone pairs did you have on the central iodine? 1. Let's see. Does that, do I agree with that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So you said 2 pairs or 1 pair? 2 pairs, right? So 2 lone pairs. And so this is the geometry, so it's called T-shape, but again, you don't have to know this, it's more for your fun facts. I think we'll have to stop there. All right, so let's go ahead. We'll take our 10-minute break, then we'll do our quiz, and then you'll will be free to work on whatever you need to, ask questions, or run away if you're good with everything. So Thursday, we'll look at naming, and then we'll just keep practicing and looking at structures. All right, so take your 10-minute break, and we'll be back. I will stop this stream.